Good afternoon, everyone. I am Waraporn Boonsupthip from Assoc University. I'm very glad that I can join your international meeting today. My topic of research that I would like to share with you today is the topic of vacuum impregnation technology for food product development. So in my lab, actually, we've been using this vacuum impregnation. In short, we call it VI. This technology, we use it to develop new products and also new process. I would like to share you some of our laboratory results. First of all, I'd like to introduce you the vacuum impregnation technology. Actually, it is a food processing technique that's very powerful. We use vacuum by creating vacuum by using a pump to force a liquid into a porous structure of food. So basically, we put solid food into the liquid in a closed chamber, and then we apply vacuum so to force the liquid, for this one, for example, the blue liquid to be forced in the solid food. After this VI, a vacuum impregnation process, we can force the blue liquid substance into the solid matrix of the food. Then at the end we get a very good food product with the liquid inside the solid matrix. To apply this technique, we have to be very careful in terms of optimizing the vacuum pump and optimizing the food and the liquid properties to get the final product in the quality that we want, like the texture, we want soft or we want strong textures, or we want how much of the liquid to get inside and how deep the depth that the liquid can go into the food matrix. This we have to design the process that fit to the food product at the end that we want. The key things to tell us that the food can be using with the vacuum impregnation to push the substance inside the solid food or not is that the characteristic of pores. Food must contain the pore that we called open pore. So the pore have to have the open area to the surface. Like this one we call open pore. Like this one we also call open pore because it has open at the surface of the solid food. This is the open pore. We have another type of pores which is we call a closed pore. For example, this one, or this one, and this one we call the closed pore because these type of pores do not have the open access to the surface of the solid food matrix here. As you can see, if we apply VI or we simply put this food matrix in a liquid, this is a clean liquid, right? Even we use VI, so we can put obviously the clean liquid into the open pore only. The closed pore, the liquid cannot get into. So technically, before we using or applying vacuum impregnation, we have to study first to see if the given food product that we want to apply with the vacuum impregnation technique has pores, open pores or not. So basically, for example, I will show you some of the picture of the pore of some food. For example, zucchini, carrot, or mushroom. As you can see, different type of food have a different size or shape or characters of pores. Like zucchini have quite small pore and have this is at the peel, so peel they are very tight kind of cells, so don't have really open access. So actually if you use the whole piece of zucchini, it would be very difficult to push the liquid inside the zucchini. But if you peel out the surface to open this kind of pore to the surface of the zucchini, then you can get liquid inside the zucchini matrix very easy. For carrot, you see is the cells of carrot kind of packed very tightly, so it's very difficult to push liquid inside the carrot matrix. On the other hand, the mushroom, as you can see, the cells of mushrooms kind of tie up very loosely, so a mushroom is very perfect sample to do to get the liquid inside the mushroom. Buying, using VI or not VI, I think it's for mushroom it's very easy because the cell is very loose. This one I like to show you some of the instrument, the system of the vacuum impregnation. Actually it's being used in home scale also. This quite small, have a closed chamber and vacuum pump. Then you can apply this technique already. It's very simple but very powerful. This is, you can buy it to use at home, or this one we have as a bigger scale, as a pilot scale we have in our lab to to do the vacuum impregnation work. And also they have a very large scale for food factory also. So this technique is available for use now also. So let me share you some of the work in our lab. We try to apply the vacuum impregnation to develop frozen mango, to make it have a good quality of frozen mango. So we define that the big issue of frozen mango is that for mangoes, the ripened one, the ripened mangoes, the texture is the color is yellow and the texture is very soft and the taste is sweet, a little sour, but more of the sweet, and have a fully aroma of mangoes. So but once you put the fresh ripe mango into frozen form, once you freeze the ripe mango, and if you eat it just like the frozen form as ice cream, it's fine. But once you thaw or you let the ice melt, so the structure of the ripe mango will get so mushy, soggy. Structure is very bad, so get very soft. So because the structure is been damaged by the ice crystal that form during freezing preservation, so this is the really big issue. It's very difficult to sell such damaged texture kind of ripe mango. So we proposed a solution using a vacuum impregnation technique. But before using that, we have to manage the ripening process of the mangoes also. So we found that if we divide the mango into like ripening process of several days, so the first day is like this just 0 day. First day it's begin with the green mango. After let it ripen for 1 day, it gets more yellow, and second day and third day and fourth day. So basically the ripening process developed quite fast, and then we found that normally when we eat raw, but like we eat fresh, people prefer to for the mango at the fourth day. But the fourth day, so the texture is very soft and sweetness and flavor fully developed. But the texture is too soft, so in the freezing industry normally they use mango on the third day, so the texture is a little bit stronger, but of course the flavor and everything will be lower than the fourth day. But right now in our research we proposing even shorter ripening process, so we suggest to use the second day. Why? I will show you why we want to use the second day. The key thing is it's just the texture that we want to preserve from the ice crystal, right? So our assumption is that if we begin with a stronger, firmer texture of ripe mango, at the end after freeze and thaw, the mango will have better texture, right? So as we study the characteristic change over the ripening process of the mango, you see the x-axis begin with the 0 day, first, second, third, fourth day, 0, first, second, third, and fourth day, and you see the color we observe. We have the getting darker, getting more yellow and more red color over the ripening time. And we observe also the total soluble solid content is keep increasing along the ripening process, and also the sweetness exponentially there, and then quite smooth out. So on the fourth day, right, and the mango flavor is very similar to the sweetness, and then the pH is increasing, meaning sourness is reducing, and the firmness much reduced after the first day, and continuously but slower reduction of the firmness of the texture, right? So from this information, as you can see, that's very clear that okay, when people love when you have the ripe mango fresh, you prefer the mango on the fourth day. That means you get a very high total soluble solid content, get very sweet, it get very high mango flavor, and reduce the sourness, but and get soft, and you like it soft when it's ripened, right? But not soggy, like soft like that, but still have kind of really good mango texture, fresh textures. So after the fourth day, yes, okay, to have it fresh, you get very best quality. So but right now the frozen industry using mango as a material, using at the the mango ripen on the third day. So the quality is quite similar on the fourth day, not as equal, but very similar. But we proposing, as you can see, the second day instead of the third day, right? The second day, the TSS it's quite a little bit smaller, sweetness lower, flavor lower, slightly higher sour, and the firmness slightly higher, right? So we're proposing to use this one because we hope that firmer structure at the beginning will get better frozen, and sour mango at the end. So, but we noticed that if we begin with the second day ripened mango, we have to end up with the very bad sweetness and flavor. So we've solved this problem by using extracting the liquid from the mango that's been dried for 4 days. We extract the liquid so we get flavor and sweetness, and we also increase the sweetness of the liquid, mango liquid that ripe on the 4th day. We get the liquid, and then of the mango liquid, and then also adding more of the sweetness by adding some sugar, and then mix it well, and then push this liquid that we extract into the matrix of the mangoes that we being incubated only 2 days. And see, we found that amazingly that we do the test by eating it. Okay, so we call it sensory test. So when we have the panelists to eat it, to taste it, and evaluate in terms of how much they like the mango for colors and odor of flavor and taste and texture and overall. So it's turned out that okay, this one, the mango that's being ripe for 3 days, and this one mangoes that's ripe for 2 days. This one before we add the liquid of the extract from the mangoes, right? So the fresh one, of course, as you can see, the color for 2 days it's lower score, meaning less like, so people prefer the 3rd day because it have higher score. For odor also higher score, taste higher score, texture higher score, and overall much higher score like 8.8, and the 2nd day having only 4.3. So then we add using VI, vacuum impregnation, to vacuum the mango liquid that we extract from the mango for 4-day ripening. So after we add in and we do the sensory test again, you see we get the color is not so good, not acceptable, but the odor increased from 5 to 7, which very close to odor the 3rd day, and this one increased from 3 to almost 8, and this one texture is a little bit softer because of the vacuum impregnation impact on the texture, and overall is much higher than not vacuum impregnated with the mango liquid. Then we do freezing and do thawing of this mango sample, and we found that very interesting result that okay, after we VI and freeze it and thaw it, and then we take the compared to the mango, which is ripe for 3 days, freeze it and thaw it, and then do the sensory testing again. As you can see that we have much better sensory score than using the 3-day ripe mango. So we quite succeeded in terms of using VI technique and selecting mango with a shorter ripening time because of better texture, and so with the color and the flavor with adding the mangoes liquid ripened for 4 days. That is much better result of the frozen mango. So we, aside from the sensory test, we also do some other tests. For example, like we measure the texture using force punching into the mango meat, and higher force for the VI sample better than the 3-day ripe mango after frozen and thaw. So we get stronger texture, and the dip loss is lower. You see the dip loss is lower for the mango which the VI process. So we conclude that using the mango that ripe only 2 days and help with the VI of the liquid from the mango ripened for 4 days can give you a better quality of frozen mango and eating as fresh after thawing. So this is some pictures of our product and some conclusion, and we also trying vacuum impregnation technique to develop some other food. This is some example to apply with rice grain. So rice grains, and normally sometimes we want to add some color, some flavor into the rice grain. This one we try to use VI and optimize it, because normally when you apply the liquid into the rice grain, rice normally crack, so almost like 100% crack. So with VI we can develop very good VI process and get very small crack, less than 10%. Okay. And also we have tried to even put using VI to put oil into starch granule. It's a rice starch granule which is actually very packed, tightly packed, very difficult to get liquid inside, especially the hydrophobic compounds like oil. So we managed to use develop the VI vacuum impregnation technique to push oil to go inside the starch granule, which allow the oil and amylose and amylopectin to interact to each other much better to create some like resistant starch and something you can change the property which more easily when you have things that can interact with amylose and amylopectin easier in the starch granule. So basically we have a lot of publication, we have books, and we also have papers on vacuum impregnation. If you're interested in, you can look through my as references. Okay, so I would end my presentation here. I would like to thank everyone for being here, and thank you Kyoto Sangyo University that having arranged a lot of excellent activities and exchange and allow us Kasetsart University to join your great activity. And also thankful very much for Professor Kyoto Kato that was very kind and very good to arrange all the good activity. Thank you so much. Next, I would like to share you some of the video that we have from our Faculty of Agroindustry. It will introduce you to know a little bit more of us, and I hope that you like to come to exchange as a student or professor exchange to Kasetsart University. So please enjoy the video. Thank you so much. And I'll wait for you to come to Kasetsart University so we can have more of the activity exchange. Thank you.